love to share my screens and just show you the lineup of videos we have here coming up. So let me show this. This is the lineup. So we have 4 sessions with some oldies but goodies, and then some very, very recent interviews with some of the map and macroscope makers. In this next hour, you will get to see, among others, a CNS video introduction, so behind the scenes. We have a TEDx in Bloomington talk on map and macroscopes. We have Visit the Gallery, a guided tour of places and spaces. We have the Humanexus 2013 version. That's a 12-minute movie on human communications throughout the ages, award-winning. Then there's the making of Humanexus, which actually was recorded in our IU cinema. And then we have an interview with Mark Smith, one of our valued map makers. We have the illuminated diagram, which many of you know, and which is also on display in Ladue Hall. We have a session on Amadria in Ladue Hall. And then we have an interview with Kara Longley, which was another artist we collaborated with on the shape of science. So please join us for this amazing compilation that Todd did for us all. And Todd is going to play the videos. Please enjoy.
Yes, and here we go.
Thousands of years, humanity has collected data. Being explorers by nature, we conquer uncharted territories. But in the oceans of information, where are the islands of wisdom and the bridges that connect them? Today, we are exposed to so much information daily. How can we prevent ourselves from losing all orientation? We are the cyber infrastructure for Network Science Center, and we have made it our business to empower people in their efforts to make sense of data.
In the information age, data visualization literacy, the ability to read and make data visualizations, is as important as being able.
Hey, Todd, I just lost sound.
Is a fun challenge.
Earth is home to billions of capable minds. Empowered by tools that render data into insights, we can address the important issues of our time. We are proud to serve today's and tomorrow's explorers.
Every morning we jump out of bed and we dive into a flood of data. Friends might have texted us, there are always more emails and tweets and Facebook updates. Some of us also have to keep track of papers, patents, grants, clinical trials data. And we need all this data to make informed decisions, to swim in grace in this flood of data, and to ultimately try to also stay sane. However, none of us was designed to deal with this flood of data. We are optimized to make local, very daily decisions. Yet there are very important long-term decisions that we have to make in our life, such as what to study, what job to take, whom to marry, and how to devote our resources and time and passion. Fortunately, there are now tools that help us make sense of massive amounts of data, that help us render this data into maps, into visualizations that not only experts, but also general audiences can understand. And colleagues of and I, we have been creating and curating the Places and Spaces Mapping Science exhibit over the last years. And this effort is a 10-year effort to bring these maps, these new maps of our collective knowledge to a general audience. We are now in the 8th year, and we have altogether 80 maps, which you see in very small thumbnail images behind me. The real maps are 24 by 30 inch large, 300 dpi. Many of them, by the way, are online, so you can explore them online. And many of them have interactive counterparts. And these maps have been created by more than 200 map makers around the globe. Each year, the exhibit, go one back, the exhibit has a theme. The very first iteration of the exhibit is on the power of maps, if you can go one back. The second iteration is on the power of reference systems. The third iteration is on the power of forecasts. Can we actually forecast science? And so in the first iteration, you get to compare and contrast first maps of our planet to the very first maps of science. And as you know, the very first maps of our planet were not perfectly accurate. And still they help people find prosperous lands, to avoid monsters like the Krampus, and to find their way home. Maps by Moll, like the one you should see now, have been designed not even 300 years ago. And they show California still as an island. And the outer coastline of Australia is not fully known, and it's only partially drawn. And I just wish that today's map makers would be as honest and simply leave out the data which is too uncertain or which they don't have, or draw a big cloud on top of it. Some of the maps in the exhibit are very personal. This is a map by a PhD student who couldn't explain to his advisor what his PhD thesis is about. And he tried for quite a while, and at the end gave up, went to the next big city just to have a good time and envision the next project. But in that city, he saw a subway map, and he realized that he can represent all the many trains of thought, complete with knowledge transfer and train exchange points as a subway map. And his advisor happens to be a big fan of subway maps. And the maker of this map is now Dr. Keith Nesbitt. Other maps use advanced data mining and visualization techniques to render an entire science by visual means. Here you have a map created from abstracts submitted to the annual meeting of the American Association for the Geography. So you have 22,000 abstracts, and he trained a neural network model to render these abstract using its self-organizing map. And after much training, each of these abstracts that share a lot of words in common are closer together, and they constitute these mountains which you see here. And each mountain is labeled by the most frequently occurring keyword, and it's rendered ultimately using a GIS system. So you see the mountains, and these are the areas which geographers study, such as population studies, migration studies, community studies. Geographers also study women. And there is this green valley to the left of you, which is puzzling because those are abstracts which are very dissimilar to each other. And it's not really clear if this is the valley of the lost and confused, authors and their abstracts, or if this is an area where the sediments of the surrounding mountains come down and create a very fertile, fruitful research environment for potentially very interdisciplinary and very path-breaking research. Other maps in the exhibit show us how connected we all are. This work by Kolitsa and Vespignani tries to predict and ultimately prevent the next pandemic influenza. As you might know, diseases in former times, they used to travel in waves, about 200 to 400 miles a year. Here you see an example of Black Death in the 14th century. In today's time and age, our diseases and us travel very conveniently via the airline transportation system. And they travel to urban centers and from there out to more rural areas. So the models which Kolitsa and Vespignani developed, they take into account not only when and where an outbreak occurs, but also how infectious this disease is. And you can then use these models to try to predict the result of different intervention strategies. So for instance, should the US use all of the vaccines just in the US, or should you share them globally? And it turns out that if they are shared globally, there are actually going to be less fatalities in the US. By the way, similar models have now been applied also to study the diffusion of ideas and of innovations. In the exhibit, you also have a map by Bart Shelley on the history of science fiction. And I hope you get to check it out and like to zoom into these areas. You might see your favorite sci-fi, Roman, or you might be seeing new topics to explore. Also part of the exhibit is a map of all the video lectures of the Khan Academy. And you get to see the topical space of all these free lectures that are now available to anyone. But you also get to see how long they are and how often they have been downloaded. And I truly hope that the call for maps for next year's iteration of the exhibit shows and attracts a map that shows us the space of all these massively open online courses, the MOOCs, so that we all get a better understanding of what kind of combination of courses might get us the next degree or the expertise we always wanted to have. The exhibit features 73 other maps and also interactive elements, some of which you see here. The exhibit has been on display in 194 venues so far. These are libraries, these are science museums, these are national academies. It's currently on display at the National Academy of Science in DC. And we have 44 exhibit advisors around the globe, which any one of you can contact to bring the exhibit to a place near you. Many of the maps you just saw have been designed using advanced data mining and visualization techniques. And my team and I, we have been working very hard to create open data, open code, and open courses so that any one of you can create your own maps. And so I believe that anyone can cook and any one of you also can map, or both can definitely be learned easily. Try it. It's actually fun. So we have been created what we call macroscopes. I assume you are familiar with microscopes and telescopes that help you to see things that are too small or too far away to be seen with your naked eyes. Macroscopes, inspired by Rosnet's futuristic science writings, they help you to see structure and patterns and trends in large amounts of data. While microscopes and telescopes are typically static instruments, these macroscopes are continuously evolving bundles of software plugins. So you can actually take an empty plate or an empty shell and you put your favorite data readers in, those that read your email or your spreadsheets. And then you go over to the next tray and you get your favorite data cleaning, data mining algorithms. And you go over to the next tray and you get your favorite visualization tools and design tools. And then you bundle it all up, you give it your own name, Kati Stream tool, for instance, and you're ready to go to analyze your own data. And we benefit deeply here from OSGI, the Open Service Gateway Initiative software standard. More than 100,000 students, researchers, and practitioners have been downloading these tools, and they're using them to answer when, where, what, and with whom questions, using temporal, geospatial, topical, and network analysis algorithms. The information visualization MOOC at Indiana University makes it even easier for you to embrace and try out these new tools. We have students from 93 countries registered. Among them are 300 faculty members, so it's not just me teaching, actually. It's a lot of other faculty members pitching in. And if you want to just see what we are doing, use the IBMOOC tag to check out on Flickr and Twitter a real life data feed of the best visualizations, the best tools, the best jobs. There are many jobs that actually need this kind of skill, and also the best company doing research and development in that area. So go have fun with maps and macroscopes, then come back and share data, share your code, share your insights, because we all need this insight to make better local and global, but also better short-term and long-term decisions. Thank you. Places and Spaces was created to demonstrate the power of maps to navigate physical places, but also abstract topical spaces. My name is Kati Börner. I am the co-curator of the exhibit together with Deborah McPherson. I'm an associate professor at the School of Library and Information Science at Indiana University. What we wanted to achieve is that we introduce people to maps of science in a way that reminds them of their usage of cartographic maps. And similarly, you can use abstract topic maps to see what kind of emerging research frontiers exist, what major researchers and papers and patents and grants exist in a certain area of research, and in general, to get a more global view of what we collectively know.
My name is Deborah McPherson, Debbie, and I am the co-curator with Kati Börner. My interest is to do with how regular people, just, the general public, a teacher, could use maps of science. You've got all these people that make maps, and there's interest in how maps can help National Science Foundation and other people with their policies and understanding how science goes together. What I want to do is be able to make them that regular people can understand how to dial into them, how to move through them. And that's the point of these themes, is to keep addressing a new topic each time until it ends up that there is this little collection of maps. And if somebody was to ask, what do you mean mapping science? Like, what is that? You would, here's some examples. Here's what we mean by reference system. Here's what we mean by this.
My name is John Ganley, and I'm Assistant Director at the Science, Industry, and Business Library of New York Public Library. The exhibit that we're doing is in keeping with our responsibility at the New York Public Library for being the central focus for science materials within the library. I worked with Kati Börner and Deborah McPherson to create the exhibit, Places and Spaces.
This is the first iteration of the Places and Spaces exhibit. It compares and contrasts first maps of our planet to first maps of sciences. The first maps of our planet were not perfectly accurate, as people just started to explore all the different continents. And it is interesting to see that in some cases they just didn't know how to complete certain shapes. Similar in today's maps of science, we know we don't have the complete and coverage and the high coverage of the data which we would like to have. And therefore, the maps of sciences which we create today cannot be complete and as correct as they should be. The second iteration of the exhibit compares and contrasts reference systems. We are interested to create a reference system of sciences, which then can be used to overlay other types of data, such as the research portfolios of different institutions or countries. They can also be used to identify and show research frontiers.
My name is Kevin Boyack. I work at Sandia National Laboratories in Albuquerque, New Mexico. And I'm actually in one of the high performance computing groups there. I actually have two maps that are co-authored with Dick Clavins in this exhibit. One of them is called The Structure of Science, and the second one is called Paradigms of Science. This is our first map, or a map that was in the first iteration of Places and Spaces, and it shows the structure of science in kind of a galaxy type form. One thing that's interesting is that this map showing science in a disciplinary fashion allows you to look at the distribution of a particular topic over the entire map of science. And so, for instance, this little cutout here shows nanotechnology, and it shows that it's centered in the physical chemistry and physics and materials area. You can see little bitty red dots spreading out through other spots in science, for instance, into biochemistry and down into medicine. This is our next iteration that appears here in the second iteration of the Places and Spaces exhibit. And we took a different tack with this map. What you see here are about 800 different circles that show sets of papers rather than sets of journals. And this map is something that we're now using to overlay other information. For instance, we can generate networks that show national strengths, national science strategies. We can generate funding profiles of different agencies. And a funding profile for NIH, for example, would show lots of money going into the biomedical areas. A funding profile for the National Science Foundation would show lots of money going in physics and chemistry. We hope that a map like this in the future can be used for educational purposes.
My name's Brad Bailey. I'm a designer who specializes in massive amounts of information. And what we have here, fitting in with the rest of the show, is a map of science showing how the different areas of science relate to the different areas of the world, as well as to one another. It's using a relatively innovative display technology called an illuminated diagram, which is an old-fashioned print and a projector that's controlled by a computer, projecting light onto the print to help direct your attention to specific issues. This particular print is showing a map of 776 different specific areas in science. Dick Clavins and Kevin Boyack did the analysis and the initial layout of these nodes here. And what we're looking at is each different spot is a separate area of science. The reason it's laid out in a ring here is really interesting. It isn't laid out because Dick and Kevin and I wanted it to be in a ring. The way that we allowed the nodes to lay themselves out is we said, if you are related, then keep them close. But if you're not terribly related, for instance, chemistry is not terribly related to the social sciences, then it allowed, then the layout algorithm allowed these things to spread out. It's called a force-directed placement algorithm. What we're doing with the illuminated diagram for this is we're lighting up the nodes. So right now it's coming through chemistry, and this is the more theoretical chemistry that's dealing with genomics. And that's causing lights to appear on this geographic map. But you'll notice that certain areas are lighting up. What's happening is as a certain area of science lights up on the other map, we light up only the places in the world that deal with that science. So this is a way of linking the two maps together. This is an abstract map. It's a map of the abstract concepts of different areas of science and how they're related. And it's very different from the very concrete map that we're all familiar with, a map of the world, which is really about real space. If I had to describe these several hundred different areas of science and say, remember this one, now remember this one, now remember this one, and this one relates to this, and this one relates to this, you can see that you couldn't possibly begin to hold all that in your mind at once. The reason you would map science or any abstract concept in general is to take advantage of your innate ability to deal with space as a foundation. And then on top of that foundation, do your analysis. So here in this lectern, we modified it by sticking a touch screen in. And I can touch the small version of this map, and I can say, what areas of science do I want to light up? And run my finger over those areas of science. And you'll notice as I run my finger over those areas of science, different parts of the globe light up. So we can focus on a certain area of science too by limiting this to chemistry, for instance. If we touch this button, it's going to show on the maps and down here only those nodes that are studying chemistry. Now we can look in both places and see how chemistry relates to the rest of the world.
My name is Dick Clavins. My interest really is trying to understand the structure of knowledge presented in a visual way that corresponds to the way knowledge actually is structured, to really get a really accurate representation, as accurate as possible, of how science is organized, all the different parts of science, and something that would be useful to a number of different users. I think There was a dream many years ago when I first heard about it was from a fellow by the name of DeSola Price, that it would be possible to actually have a map for exploration for a variety of purposes, just like a physical map of how knowledge is organized. And actually, I think its first applications was intended was for planning, government planning, to decide what areas to invest in and what areas not to invest in. The idea of the physical analogy, especially to something that responds to our eyes or visually, I think is very important, because as humans, we really, I think, get a lot more insights through the visual cues and seeing unusual patterns. From early being able to see what's on the savannah as threats and opportunities, I think we process information far better than that in most of the other mechanisms that we have. And so this is a way to be able to take extremely complex information and yet present it in a way so that the unimportant details go into the back, the really important structural elements come to the front.
Andres Cupin, Department of Geography, San Diego State University, and moved there recently from the University of New Orleans. The problem is that there's an ever increasing number of outlets for scientific publication, and just the number of publications themselves as well. And so it's increasingly hard for scientists to keep track of the latest developments, and particular with respect to the growing interdisciplinary nature of science. So it's not enough anymore to just know the publications in your own field. You have to keep track of all kinds of other fields if you really want to work on the cutting edge. And that makes it increasingly, if you combine that with the growing number of outlets and publications, it's virtually impossible for you to actually read every single article that might be relevant. So we need new tools to gain, first of all, an overview of the structure of a scientific domain like geography or geology or mathematics, as well as the structure of science as a whole. And then we can also use visualization to, for instance, find information. So we can use visualization in terms of search and navigation, as well as exploration of science as a whole or of parts of science.
I'm Henry Small, and the name of my project is Mapping Science, and I work in Philadelphia at Thomson Scientific, which used to be called the Institute for Scientific Information, and changed ownership, and now it's called Thomson Scientific. And we generate the database that's used in many of these mapping exercises, called the Science Citation Index. And on the web, it's called the Web of Science. It is an index of all the scientific literature in the world. Well, I think you have to understand, the makers of science maps are very much in the early stages of their evolution. There are no accepted standards. There are no equivalents of Mercator projections for science or any of the common things that you see in geography. And you also have to understand that mapping science is not necessarily a common sense sort of notion, because fields of science don't necessarily have a location. The locations that we assign to different fields can be completely artificial in the minds of some people, or they can be concrete. So mapping science is more of a mental map than it is a physical map. And the whole objective here, in my opinion, is to see if we can meaningfully understand the structure of science.
As a geographer, one thing that I'm very interested and excited about is that we can maybe use visualizations of science in science education, K through 12 and above and below, where science feels today very nebulous, very tough, hard to grasp for children and students at all levels. And if we make science more exciting by making these maps of them, we could, for instance, induce what you might call a sense of place in science, that students see, this is the structure of science, and there are these places, very real places in science, things that people do, and I might find a home in that place or in that place. So that's one of the promising aspects of it as well.
Was willst du? Ist das, was du willst?
これでいいでしょうか。我々
Est-ce
何を
que c'est
望んで
ça
いる
que
でしょう
nous
か。
voulons? Is this what we want? What do we want?
¿Es esto lo que queremos? ¿Qué queremos?
Is this what
Это
we
то,
want?
что мы хотим.
What do we want?
Что мы
Is
хотим?
this what we want? What do we want?
Est-ce que c'est ça que nous voulons? Qu'est-ce que nous voulons?
Do you want this? What do you want?
Is this what we want? What do we want?
È questo che vogliamo? Cos'è che vogliamo? Is this what we want? What do we want?
이게 우리가 원하는 게 맞아? 우리가 원하는 게 뭐야?
Nee, Jean, you and Kish.
Well, I'm Mark Smith. I'm a sociologist, and I've been studying the shape of online communities or social media for many years. So from a sociological perspective, the internet's been a great boon. It's an opportunity to study groups at scale that really was never available before. So my motivating question is, what do they look like? If I tell you that thousands of people have gathered in front of City Hall, somebody is likely to say, send a photographer. And that photograph might actually end up on the front page of a newspaper. It's a meaningful artifact. But every minute of every day, thousands of people are gathering in social media. Show me the photo. What does that look like? We'd like to explore what are the tools, what are the methods that are necessary to take pictures of virtual crowds. So the beauty of information visualization is that most human beings come equipped with the means of finding difference, of finding pattern in a visual image. And they may not have that ability when presented with that data quantitatively. And so information visualization is a really important part of the big data movement. And it's a part I think we should note is the most humanist part of big data, because information visualization assumes a human being. There are no information visualizations that are then fed back into computers. They don't need it. This is about computers bridging the gap to the human. And that means that somebody's got a job. It means somebody is the person for whom this information is being directed. In a lot of big data systems now, the data feeds more data, and there is no human in the loop. And so information visualization is one of the most humanist corners of the computer sciences, because it inherently is about the delivery of information to a human being rather than to another information system. What I think information visualization then has to do is move towards those things that only humans can do, and only can do with the assistance of information visualization. So computers are not bad. Computers without people seem pointless. Computers with people seem like great tools. And so I would like to see more technology that enhances the value of the human rather than minimizes the value of the human. Because we've been here about 1.5 million years. We might have a few tricks up our sleeves. There might be something very special about human that we might want to extract and amplify rather than replace.
So I've got my essay written and I've been working on it for about a week. So now I'm going to
Any story like this starts with pain. Shared pain, because suffering is soul making. And that perhaps the slight glint of friendship that is starting to emerge because we're starting to know each other and spend time together.
It's pretty awesome. You know, I was walking under and I was like, it's just like no problem, but it's pretty nice so far.
Biggest challenge for me in this project so far? I don't know. It's all a challenge.
Keeping up with the number of small components, gathering volunteers.
Like there are electronics and chemistry and metabolism and the scaffolding structure.
Are you taking video right now or just pictures? Video.
Actually, we've been very successful with the sphere so far and having everything working perfectly first time, which is kind of rare.
What are you looking forward to the most?
Besides sleeping, looking forward to seeing it all lit up and done. Seeing some of the local and neighbor behaviors that we've been talking about for so long. Looking forward to seeing it come alive.
Kind of stuck in here, so.
We are taking thingies of thingies.
The success with Amatria is when the lights go down and the sculpture is lit and it comes to life. Watching people's reactions, that's for me the biggest thing. And to have it here and to know that it's going to be here continuously, exposed to all of these students and inspiring them and inspiring us to ask bigger questions. That's probably my biggest success with Amatria.
The relationship between art and science is, it's complex in that both fields rely on an audience to make an impact. As an artist, the ability to collaborate with a scientist, it increases my audience and my impact exponentially, and gives me inspiration to communicate in a way that I hadn't before. The basic form of the sculpture represents data growth. So if a viewer were to read the sculpture from bottom to top, it represents a timeline, with the bottom of the sculpture being in the past and the top of the sculpture being contemporary times or the present. The little toadstool platforms that grow out from the vertical trunk represent scientific fields. In theory, the fields grew out of philosophy. So philosophy is the platform at the very bottom. Then as the viewer's eyes move up, fields like biology, mathematics, medicine start to emerge. And when you reach the top, the data growth is exponential. So the form is very top heavy. I actually have a difficult time expressing my ideas in 2 dimensions. When I can work in all 3, height, width, and depth, I feel more challenged. I feel like I can hold a viewer's attention for a longer time, and there's a longer read on 3-dimensional artwork. Clay gives me great ability to express and mimic all kinds of different materials. So I'm mostly attracted to clay. that's why I feel sculpture is so great for visualizing data growth and information in a way that video and text cannot. There's a new layer of communication there, the tactile, there's different types of learners, and some folks learn through tactile communication. So it was important to Dr. Borner and I, when we were discussing this sculpture, that the viewers be able to interact with the piece, that it wasn't just a static form sitting in the gallery. So the marbles reinforce the idea of the interconnectedness of all of the fields. So as the marble travels around the sculpture, it connects the different fields. Fields don't stand alone, they depend on one another. And it also reinforces the idea of growth of data over time. So the marble will eventually travel down to the platform that represents philosophy. Before this collaboration, when I was creating pieces, planning to create pieces, I considered the principles of design. The color, the form, the pattern, how the viewer's eye was going to move around the piece. But it was guided more by aesthetic principles. After collaborating with Dr. Borner and realizing that form and space and surface could be attached to data, represent data, it encouraged me to think completely differently. Just in general, I hope to never run out of ideas. Right now I have more ideas than I could make happen in a lifetime, and I hope that that's always the case. The advice I would give to young artists and scientists would be to always make connections. I'm grateful that Dr. Borner reached out to me to participate in the exhibition. It's a connection that has created a healthy level of discomfort for me as an artist, and times when I'm most uncomfortable are times when I grow the most. So my advice would be to seek out connections, and connections outside of your field.